So in this lesson, we're going to talk about the multiple linear regression model, the notation, and then we're going to start to kind of overview the multiple linear regression inference through talking about the least squares estimation and how we would get our estimated multiple linear regression equation. Let's get started. The general form for the multiple linear regression model is seen here, where we have our yi as our response, and then our x's are going to be our multiple predictors. Okay. Recall in simple linear regression, which is a special case of multiple linear regression, we would only have one predictor or only one x. Here we have k of them. Our next is, we'll look at these beta. So beta 1 through beta k, we're going to be known as our partial slopes. And this is going to measure the change in the response for 1 unit of that specific x when we hold everything else fixed. So what this is saying is, what is going to happen to y when we change x, given that we hold all the other fixed variables? So if we think back to simple linear regression, or even just algebra class, where we had y equals mxb, that m, that slope, told us how much y is changing as x increases. Same idea here. But we're going to do partial slopes. The reason we say partial is because we're holding all the other predictors fixed. The next thing that we have is our parameter of our unknown intercept. This is going to measure the mean response when all of our x's are 0. So imagine these are 0, we would only have our beta naught. This will allow us to fit our model. And in this class, we will always have an intercept in our model. There are some cases, very few, where you want it, but in our case, we will. And then our last term is our error term, which is also known as our random error or a residual error. This allows each of our response not to lay right on our population mean, and it accounts for that background noise. We also are going to make an assumption about our error, which is going to follow a normal centered at 0 and sigma squared epsilon. We're going to talk a little bit more about this assumption because it's going to really play an impact in our multiple linear regression. So some of the notation we'll be using for this lesson is little n is going to represent the number of observations, so how many data points we have. K is going to represent our number of predictors or regressors. So up here, that would be these right here, how many of those we have. And then P is going to be the number of parameters, or the number of total betas in our model. So this K is coming from all of our predictors. This +1 is coming from our intercept. If you go more into theory and you start using linear algebra, for this P is going to become more important. For our case, I'm going to keep it simple. Typically, you would go into the theory, the linear algebra, if you were doing this by hand and all that. For us, I want you guys just to know enough to, I want you guys to understand what's going on, but we will use computer to get all of our estimates and everything we'll talk about. In a simple linear, give you guys some context. In a simple linear regression, our model is y equals beta naught plus beta 1 x1, only one predictor plus epsilon. So our k is 1, but our p is 2. All right. Now, before moving into the multiple linear regression inference, I want to talk about our assumption on our epsilons, which we say follows an IID, normal, 0, sigma squared epsilon. So this assumption is going to play a lot into our multiple linear regression model. For those that didn't take Stat 5615 or need a little refresher, IID stands for independent and identically distributed. Independent means that one observation isn't going to have an impact on the next. So there's no correlation structure in our data. So if I go out and I pick up a fish, the next fish I pick up does not depend in any way on me picking that first fish. If your data does have some type of dependency, you might want to go into a more time series approach, or there are ways in which you can incorporate that type of dependency structure in your estimation. We won't talk about it though. Identically distributed just means that the mean responses all kind of follow this normal 0 sigma squared epsilon. Okay, to help us kind of get a better idea of what's going on, I drew this picture, and it's in the terms of a simple linear regression model. Where we assume our blue dots are what we observe. And then we have this, we fit a model. So this is our fitted model or a population model. Right now, it doesn't really matter to get the idea of what's going to go on. And so what this epsilon I assumption is telling us is that our error terms are normally distributed. The error term is basically allowing us so that our dots don't all line up on this red line. It's allowing and accounting for the chance that there's background noise when we collect our data, which is a reasonable assumption. And so what this is saying is that for this point right here, for this X, our noise kind of follows this distribution, where we'd expect the data to mostly be concentrated in the middle and then kind of taper off. And again, maybe let's say for this point, we'd expect it to be on this red line because the mean would be this. And then it would have some variability. Not really good at drawing normal distributions, where the majority would be centered here, and then we would taper off. So what this epsilon I is really doing is it's allowing us to have estimate and understand kind of the variability for this one point. It's making that assumption. We are going to talk a lot more about this assumption, and we're going to have to check this assumption to make sure that it's appropriate for us to do multiple linear regression. I just kind of wanted to introduce it here. We'll re-talk about it in a later lesson in the next week or so. With that in mind, we have a model. We have some assumptions we're making. Our real goal of multiple linear regression is to do some type of inference. More specifically, it is to relate the response variable to a set of predictors by using a linear equation. And what we mean by linear is linear in parameters. So this would be one statistical model that would work. Also, a model that would work is maybe yi equal to beta naught plus beta 1 x1 plus beta 2 x2 or 1 squared. This is also considered a linear equation because it's still linear in terms of our betas. What we wouldn't want is something maybe like beta naught plus epsilon beta 1 x1. This would not be linear in terms of our betas, but this would be okay. This is actually a polynomial regression. Okay, we then have our statistical model where we're trying to figure out how y is related to these x's. Once we get our statistical model, we're going to apply a least squares estimation, which will allow us to get an estimated model. Once we find our estimated model, we then want to look at the relationship between the predictors and our response so that we can evaluate the goodness of fit of our model. So we have a population model. We are now going to then estimate to figure out what these parameters are. Then we want to do some type of evaluation. How good is our model we got from our estimates to the truth? And we're going to be looking at the F-test and R-squared diagnostic. We can also do parameter inference, which relates to standard errors, hypothesis testing, confidence intervals, and we can also make predictions of the mean response and a single response prediction, which we will all talk about this week. So let's talk a little bit about what the least squares estimation is to then quickly discuss what our estimated equation is. So for the least squares estimation, we need to get estimates for our parameters. Again, up here is we're assuming our population has this model. And now our goal is to use our data and estimate what we think these betas are. We represent our estimates by putting hats on them. And so what the least squares estimate does is it tries to minimize the residual sums of squares. So it's trying to minimize what we would maybe call SSE, or residual sums of squares. Let's go to a picture to understand this a little bit better. So the whole idea is we again have these blue dots, which are our observed data. The idea of the least squares estimate is that we want to find the line, this line, that minimizes this residual difference. The residual distance is defined as the difference between what we observed and what we're going to predict for that point. Okay, so our observed would be represented as our yi, and then what we would predict would be represented as y hat I, which is really this right here. Now, again, if you recall from Stat 5615 or our mini discussion on simple linear regression, our least squares estimate has the possibility, we have a whole large possibility of lines that we could fit, right? We could fit this line representing my pen to this data. Would it make sense? No, not really, but technically you could fit this line to the data. And so what least squares estimation is doing is it's trying to find the line of best fit that's going to minimize this value. All right. To minimize this equation or our sums of squared error, we're going to take the derivative with respect to each parameter, set it equal to 0, and then solve for that parameter. Typically, again, with multiple linear regression, this is done with linear algebra and matrices. However, for you guys, we're just going to use software. I want you to at least have an idea of what least squares estimation is doing. That's why I brought it up. But to get these beta hat estimates, we're going to use software. So once you take your data, I'll show you how to put it in R jump. We're going to get estimated equation, and we're going to get our estimated values of beta naught through beta k. We're also going to get our predicted yi. Notice that in our estimated model, there isn't an epsilon. Okay, that's not here. This is our estimated model. So given data, this is what we would estimate or predict we would see. This epsilon comes into play when we're making assumptions about the population. So, quick recap. We're going to collect our data. We're going to assume a model. In this case, we're assuming a model like this. We're then going to fit our data using least squares estimation to then find our estimated equation, which is represented with hats, but no epsilon.